Just like in almost every galaxy, there is a supermassive black hole at the center of our galaxy. Sagittarius A is located about 26,000 light-years away from us and has a mass approximately 4 million times that of our Sun. Its diameter stretches across millions of kilometers, making it one of the most extreme and fascinating objects we have ever discovered in the universe. Even though we cannot see it directly, we can observe its effects on the stars and matter around it, which reveal its true presence. Although the Milky Way galaxy contains around 400 billion stars and countless planets, gas clouds, and cosmic dust, this single black hole still plays a crucial role in the structure and behavior of the galaxy. Its gravitational influence extends far beyond what we can easily imagine, affecting the motion of nearby stars and even shaping the dynamics of the galactic core. This alone is enough to understand how incredibly dense and powerful it truly is. But what makes this black hole even more extraordinary is not just its size or mass, but the fact that it is rotating at incredible speeds. The rotation speed at its equator can reach a significant fraction of the speed of light. This is not something we can easily visualize, because at such extreme speeds, the laws of physics begin to behave in ways that feel almost unreal. These speeds create powerful forces and strange distortions in the space surrounding the black hole. As the black hole spins, it doesn't just rotate on its own. It actually drags the fabric of spacetime along with it. This effect is known as frame dragging, and it means that space itself is being twisted and pulled around the black hole. Any object that gets close enough will be forced to move along with this rotation, even if no direct force is acting on it. It is as if space itself has become a moving river, carrying everything within it. The foundation of all these ideas comes from the general theory of relativity, proposed in 1915 by Albert Einstein. Before Einstein, gravity was thought of as a simple force between objects. But Einstein showed that gravity is actually the result of mass bending the fabric of spacetime. This revolutionary idea completely changed how we understand motion, energy, and the structure of the universe. Shortly after Einstein introduced his theory, Karl Schwarzschild found the first exact solution to Einstein's equations. This was a major breakthrough because it described a theoretical object where gravity becomes so strong that not even light can escape. This led to the concept of the event horizon, a boundary beyond which nothing can return. From the outside, anything crossing this boundary simply disappears forever. However, Schwarzschild's solution described a very simplified version of a black hole, one that does not rotate. In reality, this is not how black holes behave. Most black holes form from the collapse of massive stars, and these stars are already rotating before they collapse. Because of this, the resulting black hole inherits that rotation and often spins extremely fast. Over time, as the black hole consumes more matter, it can spin even faster. This is where things become far more complex. In 1963, Roy Kerr developed a solution that describes rotating black holes. This discovery revealed that the structure of a real black hole is much more complicated than previously thought. Instead of having a single point-like singularity at its center, a rotating black hole may have a ring-shaped singularity. This ring singularity introduces a completely new level of mystery. The physics in this region is not fully understood, and our current theories begin to break down. Some theoretical models suggest that this structure could allow for the existence of wormholes, potentially connecting distant parts of the universe or even entirely different universes. While these ideas are still speculative, they show just how little we truly understand about what happens inside a black hole. Another remarkable feature of rotating black holes is the existence of two event horizons. The outer event horizon is the boundary we are familiar with, the point beyond which escape is impossible. But inside that, there can be a second boundary known as the inner event horizon. In this region, the behavior of space and time becomes even more strange and unpredictable, and many of our physical laws may no longer apply in the same way. The rotation of black holes also has important consequences for objects orbiting around them. Normally, there is a minimum distance at which an object can orbit safely without falling in. However, when a black hole is rotating, this distance can change. In some cases, matter can orbit much closer to the event horizon than it would be able to around a non-rotating black hole. This leads to the formation of extremely hot and energetic accretion disks, which can shine brighter than entire galaxies. One of the most fascinating theoretical ideas related to rotating black holes is the possibility of extracting energy from them. This concept was proposed by Roger Penrose and is known as the Penrose process. According to this idea, if an object enters a specific region around the black hole called the ergosphere, it can split into two parts. One part falls into the black hole, while the other escapes with more energy than the original object had. This extra energy is not coming from nowhere. It is actually taken from the rotational energy of the black hole itself. In other words, the black hole slows down slightly as energy is extracted from it. This means that, at least in theory, black holes could be used as incredibly powerful energy sources. If an advanced civilization were capable of harnessing this process, it could potentially generate enormous amounts of energy, far beyond anything we can produce on Earth. In fact, the total rotational energy of a supermassive black hole could power entire civilizations for unimaginable lengths of time. Despite everything we have learned, black holes remain one of the greatest mysteries in modern physics. They challenge our understanding of space, time, and reality itself. Every new discovery raises even more questions, pushing the limits of what we know and what we can imagine. In the end, black holes are not just cosmic objects. They are natural laboratories where the laws of physics are pushed to their absolute limits. And as we continue to study them, we may one day uncover answers that completely change our understanding of the universe.
Thanks so much for watching my video. I really appreciate you taking the time to be here. If you enjoyed it, don't forget to leave a like and consider subscribing. It really helps the channel grow and keeps me motivated to create more content like this. Also, if you want to be notified right away whenever I upload a new video, make sure to turn on the notification bell so you don't miss anything. Thanks again for your support, and I'll see you in the next video.